Hi, this is Shoikat Mujumdar. Today we will discuss Introduction to Quantum Mechanics under the module Quantum Mechanics. The learning objective is to acquire working knowledge of the quantum mechanics postulates on the physical systems. Background. Classical theory of physics is based on some basic laws. Commonly, these are Newton's laws of motion, gravitational law of attraction between two bodies, Coulomb's law of attraction or repulsion between two electrically charged bodies, Lorentz force equation related to the force on a moving charged particle passing through a magnetic field. It has been observed that classical theory of physics can explain successfully the motion of the celestial bodies or other observable objects. There are few phenomena which the classical mechanics failed to explain. The phenomena are: number 1, stability of atom; number 2, spectral series of hydrogen atom; number 3, black body radiation. Max Planck in 1900 at a meeting of German Physical Society read his paper on the theory of the energy distribution law to the normal spectrum. This was the start of the revolution of physics, that is the start of quantum mechanics. Stability of atom. As per Rutherford's model, electrons revolve round the nucleus. This is the electron, it is revolving round the nucleus in a circular path, but particles that are in motion on a circular path would undergo acceleration. This particle will undergo acceleration, and acceleration causes radiation of energy by charged particles. So it will radiate energy. Eventually, electrons should lose energy and fall into the nucleus. As it is revolving round, one rotation after another rotation, it is losing its energy, should lose its energy, and as per Rutherford model, it should collapse onto the nucleus. But it contradicts the observed fact of the stability of atom. That means the electrons never collapse onto the nucleus. Atom is stable. Classical physics failed to explain the stability of the atom. Spectrum of the hydrogen atom. According to classical theory, an excited hydrogen atom radiates energy of all wavelengths continuously, but experimentally it has been observed that the excited atoms of hydrogen emits electromagnetic radiations of certain definite wavelengths due to transition of an electron from higher energy state to the lower energy state, corresponding to Lyman, where N1 is equal to 1, Balmer, where N1 is equal to 2, Paschen, where N1 is equal to 3, bracket N1 is equal to 4, and Hund series, where N1 is equal to 5. This discrete set of lines represented by the following formula: 1 by lambda, it is a wave number, or it may be represented as nu bar, is equal to RH. RH is the Rydberg constant. For hydrogen, its value is 1.09677576 10 to the power 7 meter inverse. Z square, RH into Z square, 1 by N1 square minus 1 by N2 square. If N1 is equal to 1, then N2 will start from 2, 3, 4. N1 is equal to 2, then N2 start from 3, 4, 5 and so on. RH is a Rydberg constant whose value is constant because of this value m e to the power 4 by 8 h cube c epsilon naught square. For heavy elements, R becomes 1.097371 into 10 to the power 7 meter inverse. This value is slightly different from hydrogen atom. In a generalization of classical physics that includes classical laws at special cases, quantum physics extends that range to the region of a small dimension. Just as c, that is the velocity of light, signifies universal constant, Planck's constant characterizes quantum physics. H is equal to 6.65 10 to the power minus 27 arc second, or 6.65 10 to the power minus 34 joule second. Particle nature of radiation. Radiation of energy is usually characterized by its wave-like nature. But many experimental observations such as blackbody radiation, photoelectric effect, Compton effect, pair production, etc. cannot be explained properly only by considering the wave nature of radiation.